Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. So today we are going to discuss the topic memory subsystem organization and interfacing. So in this lecture, we are going to cover the contents, the different types of memory chips, and then the internal chip organization and memory subsystem configuration. So these are the different contents we are going to discuss. So let's start with the memory. So memory, suppose if you consider a basic computer system, it consists of mainly three components that are CPU, central processing unit, okay, memory subsystem, input and output subsystem. So these are the three essential components of the basic computer. So here the storage memory it plays a key role. So the memory is an essential component in any general purpose computer. So it is an essential component since it is needed to store the programs and data. So in order to process the data within the computer, we need to take the data from the storage storage. So in the memory, we are storing some programs and the data. So that's why the memory it can be viewed as it is an essential component for the basic computer system. And inside the computer, we have different memories like main memory, auxiliary memory, cache memory, so like that. So main memory is the memory unit which can directly communicate with the central processing unit. So that is called main memory. And coming to the auxiliary memory. So the auxiliary memories are the devices which can be used for backup purpose. That means for future purposes, we are storing the programs and data. So such type of devices are called auxiliary memory, or auxiliary memory devices. And in auxiliary memory devices, we can store system programs, large data files, and other important backup information we can store in the auxiliary memory. And only the programs and data currently used by the CPU will be reside in the main memory, and the programs and data which are not currently used by the CPU that are stored in the this auxiliary memory. So so in this way, the used programs, the currently executing programs and data are stored in the main memory, and the unused programs and data will be stored in the auxiliary memory. So whenever the CPU requests the programs and software, then that unused programs and softwares will be copied from the auxiliary memory to the main memory whenever the CPU required. Okay, so that is a purpose of using the auxiliary memory. So auxiliary memory it can be used only for backup purposes. So this is a memory subsystem organization. Memory subsystem organization. So here we can see different types of memory devices: CPU, main memory, cache memory, I/O processor, magnetic tapes and magnetic disks. So these are magnetic tapes and magnetic disks. So these two are auxiliary memories. Okay, already we have seen why we are using the auxiliary memory. So auxiliary memories are used as for the backup purposes. And the main memory is the memory which can directly communicate with the CPU. That is called main memory. Okay, so and we are using a small amount of cache memory in between the CPU and the main memory. So here this is a main memory and it is a CPU. So in between we are using a cache memory. We are using a cache memory. So why we are using cache memory? So it is a cache memory is a it is a small amount of memory, small amount, but it is a faster. Okay. So if you consider the data transfer rates of the CPU and main memory, there is a mismatch because the CPU it can transfer the data at a faster rate. That means it can execute a million instructions per second. Okay, so if you compare the data transfer rate of the main memory with the CPU, obviously it is lesser in speed. So due to that, there is a mismatch in the data transfer rates between the CPU and the main memory. So in order to synchronize the data transfer rates between the main memory and the CPU, in between we are placing a small amount of cache memory. So this cache memory will synchronize the data transfer rate between the CPU and the main memory. So that is the use of the cache memory and IO processor. So the IO through the so we can access the auxiliary memory through the IO processors. Because so IO processors it can execute the instructions related to the input output devices. So here the main memory. So whatever the programs and the software that are currently executing, that will be executed from the main memory. So whatever the currently needed by the currently needed, the programs and the softwares will be executed from the main memory. And the programs which are not required by the CPU, that will be stored in the auxiliary memory. And whenever it is required, then that softwares and programs will be copied from the auxiliary memory to the main memory whenever the CPU required. So this is a memory subsystem organization. So coming to the types of memories in computer. So basically we have two types of memory chips that are ROM chips. ROM means read only memory, and another one is RAM, random access memory. So these are the main types of the memories. First one is ROM and the second one is RAM. Okay, so let's start with the ROM. ROM means read only memory. So that means this type of chips are designed for applications in which the data is only read. So that means using this memory chips, we can able to perform only the read operation. So we cannot write any data into the this ROM chip. So only the chip is designed only for the purpose of reading, and these chips are programmed with data by external programming unit. Okay, so these ROM chips we can program by using the some external programming unit before they are added to the computer system. So that means this ROM is available in the form of chip. So the chip, by inserting it into the ROM programmer, then we can program it. So you can see, okay. So by using the ROM programmer, we can load the program into the corresponding ROM chip. And it is a non-volatile. It is a non-volatile memory. Non-volatile means even the power supplied to the chip fails, the data stored in the memory we will not lose. So that is a non-volatile memory. And the programs and the instructions are stored by the manufacturer. So in this type of memory chips, the programs or software will be loaded by the manufacturer. Okay. So once the manufacturer is loaded the softwares and the programs into the ROM chip, we can read that programs and the software. We cannot write any information into that particular ROM chip. And also, suppose if you consider any home appliance like microwave oven or refrigerator, uh, washing machine. So these are all the different home appliances. So inside that, suppose if you consider a microwave oven, so inside that there is a ROM. So in that ROM, the program corresponding to the working of the microwave oven will be loaded, and that program will be executed. Okay. So the program corresponding to the working of the microwave oven will be loaded by the manufacturer. Once the manufacturer loaded the program into that ROM chip, as a user, we cannot erase it, and also we cannot reprogram it. Okay, so that is a ROM chip, and also in the ROM chip we can store some bootstrap program. So bootstrap program is nothing but a simple program that can be used to start the computer at the initial time. Okay, so this is a bootstrap program. So this bootstrap program, it will be loaded in the ROM memory chip, and whenever it is executing, this bootstrap program will be copied from the ROM chip to the RAM chip. From the RAM chip itself, it will be executed. So this is about the ROM chip. So if you consider a block diagram of the ROM, so here you can see. So the ROM chip size, it will be represented in m into n, m into n. So where m is equal to 2 power k into n, 2 power k into n. So where k is the number of address lines, and where n is the number of data lines. And coming to the RAM, RAM is it is also called read or write memory. Read or write memory. So that means using this RAM chip, either we can read the data from the chip, or we can also write the data into the memory. So that's why it is also called read or write memory chip. And it is a volatile memory. It is a volatile. So RAM is a volatile and ROM is a non-volatile. So volatile memory means if the power supply to the RAM chip fails, then the data stored in the RAM gets erased. So that is a volatile memory, and it can be used to store the data that changes. That means the data present in the RAM chip will be gets some modifications or gets changes, and it is not the permanent storage. So every file or application opened is placed in the RAM. So whatever if you any file or application opened, that will be executed from the RAM memory itself. And this RAM, it uses a random access technique. So random access technique means we can directly go to the any memory location inside that RAM chip. So no need to go the sequential memory locations. Okay. So here you can see the block diagram. So here the memory unit is with the 2 power k words and n bits per word. So 2 power k into n. Okay. So where k is the number of address lines and n is the number of data lines. So suppose if you consider 8 by 2 RAM chip. So 8 by 2. So that means that particular 8 by 2 RAM chip, it contains 8 memory locations. So that means this 8 we can write 2 power 3 into 2. So 2 power 3. So that means the number of address lines are 3. That means 2 power 3 is 8. That means it contains 8 memory locations. And in each memory location, we can store 2 bits of data. So that is the meaning of the 8 by 2 RAM chip. And you can see physically. So the physical structure of the RAM it looks like. And coming to the classification of the ROM chip. So here we have classified this ROM chips based on how often they can be programmed. So we have differentiated these ROM chips by how often they can be programmed. So based on that parameter, the ROM chips are classified into different types, that are mask ROM, PROM, EPROM, EEPROM, and flash EEPROM. So these are the different classification. So first one is MROM. MROM means masked read-only memory. So it is a oldest type of the memory. So in olden days we are using this type of memory. So that's why it's called oldest type of memory, ROM memory, and its contents are stored by the manufacturer during the manufacturing process. So during the manufacturing process, so the contents will be loaded into the this particular ROM chip. So once the manufacturer loaded that programs and softwares into the MROM, then the user cannot modify, cannot erase, and cannot be reprogrammed. And example is it is a consumer appliance microwave oven. So already we have seen this example, microwave oven. So this is a first type of the ROM. So masked ROM. Masked ROM means here in this the programs and data will be loaded by the manufacturer. Once the manufacturer loaded the programs and data, then the user cannot modify or cannot erase it. So this is about the MROM, masked ROM. Then the second one is PROM. PROM means programmable read-only memory. So PROM can be programmed only once by the user with any standard PROM programmer. So with this type of PROM chipper, the user can program only once. Once the user programmed, then the user cannot erasable. It cannot be erasable. So from the user can purchase a blank PROM from the market. Then we can program it by using the programmer, PROM programmer. So here you can see the PROM programmer. So this is a programmer. So by inserting that PROM chip into this slot, then we can program it. Okay. So once the program is loaded into the PROM chip, the user cannot erase it. Okay. And the example is prototyping. Prototyping purposes, then we can use this PROM chip. So in RFID tags, cell phones, video game consoles, etc., we can use. Okay. So say this is a second type of the ROM. And coming to the third one, EPROM. So EPROM means erasable and programmable read-only memory. So this EPROM can be programmed and erased many times by the user. So the user can write a program, and if any modifications are required, then he or she can erase it, then reprogram it. So like that, many times we can erasable and reprogrammable. And the contents of this EPROM can be erased by exposing this EPROM chip into the ultraviolet light by approximately 20 to 40 minutes. When you expose that EPROM chip into the ultraviolet light, then the contents inside the EPROM chip gets erased. Okay. Then it is this type of EPROMs can be useful for product development labs and prototyping purposes. And coming to the EEPROM, that means electrically erasable and programmable read-only memory. So that is called EEPROM. So that means here in this type of memory chips, we can program and we can erase by means of electrically. By applying some electrical signal, then we can able to erase the content as well as we can able to reprogram it. And by using this EEPROM, it can be programmed and erased nearly 10,000 times. 10,000 times. And both programming and erasing, it takes about 4 to 10 milliseconds. That means it is very faster. We can erase the data at a faster rate than the EEPROM, because the previous one EEPROM, it takes approximately 20 to 40 minutes to erase the entire chip, but here it takes only 4 to 10 milliseconds of time to erase the entire chip. And one more is the any location can be electrically erased. Suppose if you want to erase any particular memory location, then we can do it by using this EEPROM. So rather than erasing entire chip. So here no need to erase the entire chip. Only whatever the specific location you want to erase, that can erase by using this EEPROM. Okay, so the example is BIOS of computer. So BIOS means basic input output system. BIOS of the computer we can load in this type of EEPROM. And the last one is it is a flash EEPROM. So this is an advanced version of the EEPROM. It is an advanced version because it is a faster. It is a faster than the EEPROM. And we can write a blocks of data into at a particular time. So that means here when we are programming the flash EEPROM, then a block of data we can program into the chip at a time. But if you consider a previous one, EEPROM, so here only one byte of data we can program into the memory chip. But here in this flash EEPROM, we can program a block of data. So that's why it is a faster than the EEPROM chip. And it can be used in MP3 players, digital cameras, and modems. Okay. So these are all the different types of the ROM chips. And coming to the RAM chips, so these RAM chips are differentiated by how they maintain their data. Okay. So based on this parameter, the RAM chips are classified into the two types. One is a static RAM, static random access memory, SRAM, shortly we can call SRAM. And the second one is a DRAM, dynamic. So dynamic RAM. So these are the two types, SRAM and the DRAM. First one is a SRAM, static RAM. So the static RAM hold data without external refresh. So here in the static RAM, so we are not require any refresh cycle, because to construct this SRAM, we require a mass transistor. So here in this type of memory SRAM, we are not using any capacitor. So that's why here no need of the refreshment cycle. And it doesn't require any external refreshment circuitry, as we don't require the refreshment cycle. So here we do not require any refreshment circuits also. And SRAM is faster than DRAM. It is a faster and several times more expensive than DRAM. It is expensive because to construct the SRAM, we require more number of components. So if you look into the SRAM cell structure, so this is a SRAM cell structure. So it is a structure of a single cell in the SRAM. So in order to construct a single cell, we require 6 mass transistors that are, you can see here, M1, M2, M3, M4, M5, M6. So that means we require total 6 mass transistors in order to construct a single memory cell. So like that, we require a more number of components in order to build a SRAM chip, larger SRAM chip. So that's why obviously it is expensive than the DRAM. Suppose if you consider a DRAM cell, for the construction of this DRAM, we require only two components. One is the pass transistor, nothing but a MOSFET, and one capacitor. So that's why when you compare the complexity of the circuit SRAM with DRAM, the SRAM complexity is more, and also cost also more, and also the power consumption. So power consumption of SRAM also more, because more number of components are present inside the SRAM cell. So that's why more power consumption is required. And also when you compare the sizes, the size of the SRAM is larger than the DRAM. Okay, so here you can see the design of the static RAM SRAM. So here you can see the diagram. It is a single memory cell structure. So this memory structure cell, it consists of 6 MOS transistors, M1, M2, M3, M4. So these total 4 MOS transistors will form as a inverter, cross-coupled inverter. So that means it is a, if you look into this, it is a CMOS, NOT gate, NOT. So that means it will act as a like that. And this is another CMOS NOT gate. So these two gates, NOT gates, are connected in a cross coupled. That means output of one will be given to the input of the another gate. So they will looks like this. Okay. So these are the in order to construct this, we require 4 transistors, and the remaining transistor F5 and M5 and M6. So these transistors are called pass transistors, because in order to read or write the data into the memory cell, then we have to operate this M5 and M6 transistors. Whenever whenever the W line is equal to 1, then this M5 and M6 MOSFETs will be turned on. Then we can read the data present in the read or write the data present in the memory cell. Suppose if WL is equal to write line is equal to 0, then the pass transistors M5 and M6 both will be off state. So we cannot read or write the data from the memory cell. Okay. And coming to the design of SRAM. So this is a SRAM cell. So using this SRAM cell, either we can perform read or write operation. We can perform 2 types of operation, either read or write. So we cannot perform read and write at a time. Only we can perform one operation at a time. So when we are reading the data from the memory cell, so when we are reading the data, then the BL and BL dash lines will act as a output lines. Similarly, when we are writing the data into the memory cell, then this BL and BL bar lines will be acts as a input lines. Okay, so this is a read and write operation. So when WL is equal to 1, suppose if WL is equal to 0, that means the transistor M5 and M6, this will be turned off. If the M5 and M6 transistors are turned off, then we cannot read or write from the memory cell, because it will be disconnected from the memory cell. So that's why we cannot able to read or write the data from the memory cell. So that's why in that when the WL is equal to 0, that means the memory cell which holds the data. So when WL is equal to 1, we can perform a read or write, and when WL is equal to 0, then the memory cell will hold the data. So let's see the read operation. Okay. So in order to perform the read operation, so see, suppose consider if Q is equal to 1 and Q bar is equal to 0. So assume that the memory which holds the logic 1, Q is equal to 1 and Q bar is equal to 0. So we are reading the data. We are reading the data present in the memory cell. So in order to read or write the data from the memory cell, the word line should be WL should be it is equal to 1. So when WL is equal to 1, then the M5 and M6 transistors will be turned on. Then this BL bar and BL lines will be connected to the memory. So that means here this M6 and M5 will act as a short circuit. That means closed switch. So that this Q bar will be connected to the BL bar and Q will be connected to the BL line. Okay. So that means this BL. Okay. So that means this BL and BL bar. So these two lines will act as a output lines because we are performing a read operation. So when we are performing read operation, the BL and BL dash will act as a output lines. Then this BL and BL bar lines we are giving to a sensing amplifier. Sensing amplifier. So that means here we are giving to BL bar. Okay. So here BL is equal to 1 and BL bar is equal to 0. Then the summing amplifier will give the output as a logic 1. So that means we are reading the logic 1. Okay. So in this way we can read the data present in the memory cell. Consider the another case, that is if Q is equal to 0 and Q bar is equal to 1. So if Q is equal to 0 and Q bar is equal to 1, then we are performing a read operation. So when we are performing a read operation, WL is equal to 1. Okay. Then this M5 and M6 transistors will be turned on because we have applied a logic 1. So that the M5 and M6 transistors will be turned on, so that this one Q bar will be connected to BL and Q will be connected to the BL. So this BL and BL bar lines we are giving to the sensing amplifier. Then the sensing amplifier output will be given as the logic 0. So in this way we can read the data present in the memory cell. Similarly, we can also see the write operation. So in order to perform the write operation, the BL and BL dash lines will act as a input lines. Okay. And if BL is equal to, so that means we are writing the data into the memory cell. So what we are in BL is equal to 1 and BL dash or BL bar is equal to 0. Okay. So in order to perform write or read operation, the WL is equal to 1. So that these transistors will be M5 and M6 will be turned on. So that this 1 will be stored into the Q and 0 will be loaded into the Q bar. Okay. So in that way, the data can be write into the memory cell. And coming to the DRAM. So it is a basic storage device, is a MOSFET and the capacitor. So if you look into the SRAM structure, it requires 6 MOS transistors. But here we require only one pass transistor and one capacitor in order to construct the single memory cell. And charge determines the charge. So the charge determines the stored bit 0 or 1. So that means if the storage capacitor is fully charged, then it will be considered as a logic 1. And if the storage capacitor is completely discharged, then that can be considered as a logic 0. And the data stored as a charge cannot be remain indefinitely. So due to the leakage current, therefore periodic refreshment cycles is required in order to maintain the stored data. So if you look into the dynamic RAM cell structure, so here we are using a storage capacitor. So this is a leakage capacitor. That means the charge stored in the capacitor, it will not be retained infinitely. So that means the charge stored in the capacitor will discharge with respect to the time, because it is a leakage capacitor. Okay. So in order to maintain the charge inside the capacitor, then it requires some refreshment cycles periodically. Okay. So that's why here the DRAM it requires refreshment cycles, but whereas the SRAM it doesn't require any refreshment cycles, as it doesn't contain any capacitors. So here you can see the read operation. So in order to perform the read operation, the WL is should be 1. So WL is equal to 1. Okay. Then when you are performing a read operation, then the BL acts as a output line. BL, that means a bit line. WL means word line, BL means bit line. Okay. So when we are performing a read operation, the BL acts as a output line. So see here. So here W line is equal to logic 1. So logic 1 means here the 1 will be applied to the input of the pass transistor. So the transistor will be turned on. Okay, it will be turned on. It will be acts as a on switch. Then this capacitor will be connected to this bit line. So here this bit line here we are connecting one pre-charge capacitor. So that means initially the capacitor, pre-charge capacitor, it will be charged to the VDD by 2. So suppose if the capacitor is stored, that means this stored charge will be shared with this bit line. So that means when the pass transistor is turned on, then the charge stored in the capacitor will be shared with the pass transistor. That means the voltage at the charge at the bit line, obviously it will be more than VDD by 2. Okay. So this bit line we are giving to the sensing amplifier. Then the sensing amplifier it will give the output as a logic 1, as the output voltage, bit line voltage is more than VDD by 2. So that's why it will be the sensing amplifier will give the output as logic 1. Suppose if the capacitor is not charged, that means if the W line is equal to 1, then the pass transistor will be turned on. It acts as a on switch. Then this 0 voltage will be shared with the pre-charge capacitor. Then the charge at the bit line will be drops to less than VDD by 2. So the bit line will be given to the sensing amplifier. Then the sensing amplifier output will be given as a 0. So in this way we can read the data present in the DRAM cell. And similarly, write operation. So BL acts as the input. So BL line, bit line, it acts as a input line. Okay, so this is the input line. Suppose if you want to write logic 1 to the memory cell, then we are applying a a logic 1 to the bit line, and W line also 1. Then this transistor will be turned on, then this logic 1 will be shared with the capacitor, then the capacitor will be charged, then it will be treated as a logic 1. Similarly, logic 0. Suppose if you want to write a logic 0, then we have to apply that logic 0 to the bit line, and the W line is equal to 1. Then this pass transistor will be turned on, this logic 0 will be shared with the capacitor. So the capacitor will charge the 0, logic 0. So in this way we can perform the write operation. So coming to the internal chip organization. Okay. So the internal organization of the ROM and RAM chips are similar. In order to illustrate the simple organization, let us consider a linear organization of 8x2 ROM chip. So this is a internal chip organization. So this one. Okay. So here it requires a decoder, 3x8 decoder. So total it requires 3 address lines and 2 data lines. So that means this is a 8x2. 8x2. So 8x2 means it contains total 8 memory locations. 8 memory locations. That is 0, 1, 2, 3, 4, 5, 6, 7. So total it contains 8 memory locations, and in every memory location we can store 2 bits of data. So that means either 0, 1, 1, 0, 0, 0, 1, 0, 1, 1. So like that, in every memory location we can store some information, 2-bit information. Okay. So it contains total 8 rows and 2 columns. And here chip enable and OE. CE means chip enable and OE means output enable. Okay. So in order to read the data from the memory cell, the CE should be logic 1 and OE should be logic 1. So when the CE and chip enable and output enable pins are equal to the logic 1, then the output of the gate will be logic 1. Then this output buffer. So these are the output buffers. So these output buffers will be enabled. Then the data present in the memory cell will be outputted. Okay. So if you see here, it is a tri-state buffer. So this tri-state buffers which are connected to the memory location will be enabled to pass the data to the output buffers. Okay. So first, if the tri-state buffers are enabled, then only the data present in the memory cell will be transferred to the output buffer. And finally, with the CE and OE is equal to 1, the output buffers will be enabled. Then we can read the data with the help of the data lines D0 and D1. So this is a internal chip organization of the 8x2 ROM chip. So here, so this is suitable for the when the number of memory locations are small, but for the large number of memory locations it becomes very difficult because the decoder required will be large. So it is somewhat complicated. Okay. So as the number of memory locations increases, the size of the address decoder needed in a linear organization becomes prohibitively larger. Okay, so the memory chip can be designed using multiple dimensions of decoding. So in order to overcome that problem, we are designing the memory chip using a multiple dimensions of decoding. So for that, we consider a two-dimensional organization. Two-dimensional organization. So this configuration has 4 rows with 4 bits per row. So you can see here, this is a internal two-chip organization of 8 by 2 row. So here we have arranged 2 rows. This is 1 row, second row, third, and this is a fourth. So total it contains 4 rows, and in each row it stores 4 bits. So this is bit 1, 2, 3, 4. So that means total it contains 16 memory locations. Okay. So these rows we can decode using this address lines A1, A2, and this is a A0 in order to enable the pass transistors, in order to enable the output buffers, and the CE, OE. Okay, and coming to the memory subsystem configuration. So it is very easy to set up a memory system that consists of a single chip. And most memory systems requires more than one chip. Most memory systems, it requires more than one chip. So if 2 or more chips are there, then we can combine to create a single memory chip with more bits per location. So here you can understand this with the example 8 by 2. Two 8 by 2 chips can be combined to create a 8 by 4 memory. Okay, so that means here we are increasing the word length. So in this 8 by 2, in every memory location we can store only 2 bits of data. But here in the 8 by 4, that means we have increased the word length. That means we have increased the word length from 2 to 4. That means in every memory location we can store 4 bits of data. So this is a combining, how we can combine 2 or more memories in order to increase the word length. So this is a 8 by 2 ROM chip, and this is another 8 by 2 ROM chip. So this is a upper ROM, this is called lower ROM chip. So here it requires 3 address lines and 2. So with a single 8 by 2, we have 2 data lines. We have 2 data lines. Here we have combined the 2 8 by 2 ROM chips. So that's why, so total we have 2 plus 2, 4 data lines. That means in every memory location we can store 4 bits of data. So instead of creating wider words, the chips can be combined to create more words. So here, instead of increasing the word length, we can also increase the number of memory locations. Okay. So the same 2 8 by 2 chips could be instead be configured as a 16 by 2 memory subsystem. That means previously we have combined 2 8 by 2 chips in order to form 8 by 4 chip. But here we are combining 8 by 2. Okay, so 2 8 by 2 chips we are combining to form 16 by 2. That means we have increased the number of memory locations. So let's see how we can increase the memory locations. So this we can do with the concept memory interleaving. So memory interleaving is a technique that can divide memory into the number of modules, or we can also call we can create a a single memory by combining the all different sub memory chips. Okay, so this is called high order interleaving. High order interleaving. So for this, we require four address lines. So this is A0, A1, A2, and this is a A3. Okay. So this A3 we are giving to the CE of the first chip through the some gates, and we are giving the same A3 to here. So when A3 is equal to 0, then we can access the upper ROM. When A3 is equal to 1, then we can access the lower ROM. Okay, so we can see here. So this is so that means by combining two 8x2 ROM chips, then we can form a 16 memory locations. So 0 to 16, total 16. So we are discussing the higher order. So higher order. That means so this first two. So if you represent A0, A1, A2, A3. So this A2, A3. So these are called higher order bus. So this will divide this memory locations into sub modules. Okay. So if you look into the A2, A3 address lines, these are common for this four. So that means here the module is 0, 0, 0, 1, 1, 0, 1, 1. So when A3 is equal to 0, then so using this combination, we can access total 0 to 15 memory locations. Okay, so 0 to 7 with the upper ROM and 8 to 15 for lower ROM. Okay, so 0 to 7. That means when A3 is equal to 0, when A3 is equal to 0, when A3 is equal to 0, then these are the memory locations contained by the upper ROM. When A3 is equal to 1, the 8 to 15 memory locations will be held by the lower ROM. Okay. So based on using this higher order interleaving, so the entire total number of memory locations we are dividing into different modules. Module 00, module 01, module 10, module 11. Okay. So these are the different submodules of this memory. So that means it holds the data 0, 10, 50, 90, 130. So this is high order. And if you come to the low order interleaving, low order interleaving means with the help of lower address bit A0, we are deciding which memory chip we are accessing. So that is the meaning here. So A0 we are giving to both the ROM chips, and A1, A2, A3 we are giving to all the corresponding memory chips. Okay, so that means here, see here. So here this is A0. So A0. So A0, when A0 is equal to 0, okay, when A0 is equal to 0, the upper A0 is equal to 0, the upper ROM contains these memory locations. So that means looking here. So A0, A1, A2, A3. So here A0 is equal to 0. A0 is equal to 0 means here this is a 0 location. Second here, this one, here, this one, here. So that means when A0 is equal to 0, the upper ROM, it contains the memory locations 0, 2, 4, 6, 8, 10, 12, 14. Similarly, when A0 is equal to 1, the lower ROM, it contains the memory locations 1, 3, 5, 7, 9, 11, 13, 15. So, in this way, the memory which holds the memory locations. So, the higher order interleaving and the lower order interleaving both it seems similar, but the data access from this lower order interleaving is faster. Okay, so in this lecture we have discussed different types of ROM chips and internal chip organization and memory subsystem organization. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.